All right, so we are now familiar with what is meant by an upper triangular matrix, a lower triangular matrix, a diagonal matrix, and a symmetric matrix. Now I want us to make some observations about just some properties of these matrices if we start working with them. So to do this, let's imagine that A and B are both one of these kinds of matrices. So let's just say, for the sake of argument here to start, let A and B both be upper triangular matrices. And in particular, let them be upper triangular matrices of the same size. So in other words, A and B are both 3 by 3, or both 4 by 4, or both 5 by 5. And the reason that we're going to do this in particular is because we're going to be adding the matrices. And you know that in order to add matrices, you've got to, at a minimum, have matrices of the same size. But heck, once you have matrices of the same size, you can add them up very easily just by adding component by component. So, okay, we've got A and B, two upper triangular matrices of the same size. Note, by virtue of them being upper triangular, or for that matter, lower diagonal or symmetric, we know we got a square matrix. So when we say same size, we're talking 3 by 3, 4 by 4, 2 by 2, 5 by 5, 10 by 10, hell, 1 by 1 if you wanted it to be. But the long story short is we've got two upper triangular matrices of the same size. For the sake of visualizing this, let's just imagine both of them were 4 by 4s. So both A and B take the form of our upper triangular matrix. Now, what we want to consider is A plus B. So we want to add these two matrices together. And when you think about this, what is that going to look like? Well, here is your one upper triangular matrix. And here is your other upper triangular matrix. And we want to add these together. Well, when you would add these matrices together, note the result is also going to be upper triangular. Why is that? Well, I mean, look at the entries. To be upper triangular, you have to have all of your non-zero entries at the diagonal and above in the upper triangle. And whenever you add these two matrices together, you're always going to get zeros in the lower triangle below the diagonal, because below the diagonal, you're always adding 0 plus 0. And since 0 plus 0 is always 0, when you add two upper triangular matrices, the result is itself going to be upper triangular. Now, hey, maybe some of these non-zero entries above cancel out and become 0. That's fine, no worries, because the only restriction on our upper triangular matrix was that at the diagonal and above, that's the only position for entries that could be anything. And those entries above the diagonal, or rather at the diagonal and above, could be anything. Everything below the diagonal is forced to be 0. Now, if you think about this for a second, I mean, the fact that this summation worked in the sense that upper triangular matrices remained upper triangular when adding them together, note the same idea would hold for lower triangular matrices. Because just as with the upper triangular matrices, whenever the 0 values below the diagonal added 0 plus 0. If you added a pair of lower triangular matrices together, the 0 entries above the diagonal would add with one another and remain 0. Heck, think about this for diagonal matrices instead of lower triangular matrices. The same story plays out, doesn't it? Because if you took a diagonal matrix and another diagonal matrix and you added them up, the only positions where you could possibly have non-zero entries are along the diagonal. Because everywhere where you're not on the diagonal, both matrices have values of 0, and 0 plus 0 is 0. I mean, hell, if you want to think about it with respect to symmetric matrices, the same story would play out, wouldn't it? Now, this one may be harder to see, but if you think about it, take two symmetric matrices. Let me just, for the sake of simplicity, let's take 2 by 2 symmetric matrices. So we've got a 2 and a 5. Since we've got a 5 in position row 1, column 2, that's got to be also down in row 2, column 1. And then the 2, 2 position could be anything, so let's say it's 3. And then let's add this to a matrix. Let's go -1, 7. Since we've got a 7 in row 1, column 2, you've got to have a 7 in row 2, column 1. The long story short with the symmetric matrix is the diagonal could be anything. Everything off the diagonal is forced to be symmetric. So the diagonal could be anything. Let's just say it's 10. Well, when you add these together, the diagonal is again going to be anything. No issue there. But whatever you are looking at the positions that are off the diagonal, the positions that are off the diagonal are going to be symmetric because whatever values were in the one matrix and whatever values were in the other matrix were symmetric already. So when you add them up, the result that you get in one is going to be consistent with the position that is symmetric to it. So the long story short is this summation fact applies to symmetric matrices as well. And in general then, no matter which of these 4 types of matrices you're looking at, let A and B both be any of the 4 types, then A plus B must also be of the same type. So in other words, take 2 upper triangular matrices, add them together, the result, upper triangular. Take 2 lower triangular, add them together, the result, lower triangular. Take 2 diagonal, add them together, diagonal. Take 2 symmetric, add them together, symmetric. Now this may not seem like all that crazy of an idea in light of how these things are defined. But I mean, if you think about all of the matrices that we've discussed to this point in this class, like, I mean, as a counter example to this thought of matrices summing together to be of the same type, just as a counter example, consider elementary matrices. I claim I can take 2 elementary matrices, add them together, and get something that's not elementary. Take the matrix, let's see, 1, 0, 0, 0, 0, 1, 0, 1, 0. That is an elementary matrix. Why is it an elementary matrix? It is the identity matrix with 2 rows switched. Here's another elementary matrix. Let's go 0, 0, 1, 0, 1, 0, 1, 0, 0. Here's another elementary matrix. Why is this matrix elementary? It is the identity matrix with 2 rows switched. Whereas in the one case we had rows 2 and 3 switched, here we have rows 1 and rows 3 switched. But so be it, both of these are elementary matrices. This one corresponding to rows 2 and rows 3 switching, that one corresponding to rows 1 and row 3 switching. But here's the big idea, add them together. When you add these together, you get something which is not elementary. That is not an elementary matrix, yet that is what results from adding elementary matrices together. So an interesting thing that we can sort of observe here is that while upper triangular matrices plus upper triangular matrices remain upper triangular matrices, and lower triangular plus lower triangular remain lower triangular, same for diagonal and symmetric, the same is not true for elementary matrices. Elementary matrices can add together and no longer be elementary. But the 4 types of matrices that we've talked about today, or established today as these 4 types of square matrices, add them to each other, you always end up with the same type in return. That's kind of interesting. Actually, when you think about this as well, let's sort of like add on to this. What if you had C be some constant? Take any real number of your choice and think about what C times A would look like. I mean, we've got this upper triangular matrix down here. Imagine if you multiplied the matrix times C. Remember, C here is a number, and whenever you multiply a matrix times a number, you just distribute that number to every entry. Well, when you take C times this matrix, multiplying every entry by C, all of the possibly non-zero entries are still possibly non-zero. And more importantly, all of the 0 entries remain 0. Since 0 times any number is 0, When you take a constant times an upper triangular matrix, all of the entries that were 0 remain 0, and the result, upper triangular. When you take a lower triangular matrix, multiply it by a constant, all of the 0 entries remain 0. Diagonal, same story. Since 0 times any number is 0, then the upper, lower, and diagonal matrices all remain upper, lower, and diagonal when multiplied by a constant. What about a symmetric matrix? Symmetric matrices, every entry along the diagonal could be anything. All the entries off the diagonal have to be symmetric about that diagonal line. Well, when you take this and multiply it by a constant, all the entries along the diagonal could still be anything, and whatever the entries were that were symmetric, they're both being multiplied by c, so they're still symmetric. So the long story short is, if you're dealing with any of these types of matrices that we're talking about, upper, lower, diagonal, symmetric, whenever you multiply by a constant, the constant times that matrix is also of the same type. And again, you might say, well, so what? You know, that seems like a natural property based on the fact that these matrices are defined as they are. Well, go back to your elementary matrices as an example. Like, take the elementary matrix 1, 0, 0, 0, 1, 0, 0, 1, 0. Take the elementary matrix where row 2 and row 3 are flipped. Multiply this by some constant. That is no longer an elementary matrix. Because here, you've got row 1 multiplied by 4, row 3 swapped with row 2 and multiplied by 4, and row 2 and row 3 swapped multiplied by 4. The long story short is that's not an elementary operation. This may be a collection of elementary operations, but it is not in and of itself an elementary matrix, because an elementary matrix is an identity matrix with rows switched, or with one row added to another, or with a single row multiplied by a constant, and that is not the case here. So whereas the upper, lower, diagonal, and symmetric matrices, when you multiply by a constant, you remain of that kind, the same cannot be said for elementary matrices. And the long story short is, because of the, in some sense, nice, pleasant definitions of upper triangular matrices, lower triangular matrices, diagonal matrices, and symmetric matrices, when you add matrices of the same type together, you get something of the same type. And when you multiply by a constant, you get something of the same type back in return. And at this point, like, in the future we'll see what this ultimately means for us, but at this point, having made these observations is sufficient to sort of like just put to rest, for now at least, a basic awareness of what these matrices are and what some of their properties are as well.